A conveyor stops for 11 seconds. 12 downstream stations go idle at once. The pause was smaller than the gap it exposed. Every supply chain runs on timing. The tighter the timing, the less room exists between one step and the next. Slack is not waste. It is the system's ability to absorb surprise. Before modern logistics, warehouses held weeks of inventory. That inventory was expensive to store. It was also the reason late shipments went unnoticed. Just-in-time delivery replaced stockpiles with schedules. Each truck arrival was timed to a production window. Storage cost dropped. Tolerance for delay dropped with it. Schedules replaced inventory because schedules cost nothing to store. The system traded physical margin for temporal precision. It looked like progress. Efficiency gains were real and measurable. Less space used, less capital locked in product sitting still. The savings became the justification for removing more buffer. Suppliers adopted the same logic. They reduced their own inventory to match tighter delivery windows. Each layer of the chain compressed simultaneously. The system grew faster and thinner at once. This is the anchor facility. It processes material from 30 upstream sources. Each one arrives precisely on schedule. The building has no reserve capacity. When a system runs at full capacity continuously, it can no longer absorb variation. The same throughput that made it efficient makes it brittle. Both conditions come from the same design. The system does not know it is fragile. It only knows its current throughput. Fragility is a property that becomes visible only when the disturbance arrives. A routing gate fails at the junction. Material from two belts begins to accumulate at the merge point. Within seconds, both upstream belts are backing up. The failure did not grow. It transferred. Each station waiting for input became a waiting station. The blockage moved through the network as a shape. A system with buffer absorbs local failure without transmission. A system without buffer converts every local failure into a network event. The structure determines which kind it is. This pattern appears across many kinds of systems. The same logic that removes slack from freight also removes it from manufacturing, from utilities, from infrastructure. The substrate changes. The mechanic does not. Manufacturing plants move to lean production in sequence, not because a single decision was made, but because each facility, responding to its own cost pressure, arrived at the same answer independently. When many facilities adopt identical structures, they create a network of identical vulnerabilities. The same component fails across plants simultaneously. A shared supplier becomes a shared point of failure. Concentration is efficiency's byproduct. When sourcing consolidates to fewer suppliers for lower unit costs, the number of failure paths narrows, and each remaining path carries more weight. When a sole supplier halts production, the signal reaches every downstream plant at the same moment. There is no alternative source. The network does not reroute. It stops. The anchor facility has received its last scheduled delivery on time. It continues processing at full rate. It does not yet know that the upstream source has stopped sending. Information about disruption travels through supply chains more slowly than the disruption itself. By the time a shortage is visible, it has already been building for days. Demand signals move upstream in the opposite direction from material flow. They pass through each tier of the chain before reaching the source. At each handoff, the signal is slightly delayed. The delay between a disruption occurring and a response reaching the source is not a failure of communication. It is a structural property of the chain's length. Longer chains have longer lag. These patterns repeat across many systems over time. If you find value in understanding structures like this one, the channel covers new mechanisms regularly. A company managing inventory responds to a shortage signal by ordering more than it needs. This is not irrational. It is the correct response given uncertainty and the risk of running dry. When every company in a chain responds to the same shortage with precautionary overordering, the supplier receives a demand signal far larger than the actual shortage. The amplification is a property of the network, not of any single actor. This amplification has a name: the bullwhip effect. Small demand variation at the consumer end produces large order swings at the supplier end. The effect grows stronger as chain length increases. The supplier, receiving an amplified order, increases production capacity. New equipment is installed. Additional shifts are scheduled. The supplier is responding to a signal that does not represent actual demand. By the time the expanded capacity comes online, the downstream shortage has resolved. Companies have received their overorders. Actual demand has returned to its original level. The supplier now has excess capacity serving a need that no longer exists. The system has overshot. The overcorrection is not an error. It is the expected output of a tightly coupled network operating with information delay. The overshoot was always the probable result. A system optimized for speed cannot self-correct slowly. When it overshoots, it corrects at the same rate it expanded, which often creates the next oscillation before the first one has settled. Oscillation is not a sign of a broken system. It is the expected behavior of a system that optimized out its ability to dampen variation. The swings are structural, not accidental. The system does not respond to its own oscillation. It responds to the last observed signal. By the time the signal changes, the response is already committed. Geography adds another layer of delay. Components manufactured on one continent and consumed on another must cross weeks of transit time. That transit time is invisible inventory no one manages. At sea, a shipment does not know it has been canceled. It continues moving toward its destination even after the order it was fulfilling has been superseded by a new one. Port congestion multiplies the delay. When more ships arrive than berths can accept, vessels wait at anchor. Each day waiting represents upstream production that has already been paid for and cannot be used. The delay compounds. A ship waiting 3 days at anchor is 3 days of product that downstream facilities have scheduled to receive. Those facilities have already adjusted their production schedules around that arrival. Single-source manufacturing for critical components creates geographic concentration risk. The cost efficiency of one large factory in one location is offset by the exposure that location carries. A disruption at a geographically concentrated source, weather, infrastructure failure, or regional closure, cannot be immediately redirected. There is no parallel source designed into the system. Redundancy was removed because it produced no measurable output. A backup supplier that is never activated generates no throughput. In efficiency accounting, it does not appear as an asset. It appears as cost. When the primary source fails, the backup that was maintained on paper no longer exists in practice. The capability was allowed to atrophy. The machines are present, but the process they require has dissolved. Lean practices were not a mistake. They produced exactly what they were designed to produce: lower costs, faster throughput, and reduced waste under normal operating conditions. The problem is not that lean systems fail during disruptions. It is that lean systems are optimized exclusively for the conditions they expect. Conditions they do not expect are not in the design. Resilience requires capacity that appears idle under normal conditions. A system that uses all of its capacity all of the time has no capacity available when normal conditions change. Designing in reserve capacity has a cost that appears immediately on every operational report. The benefit of that capacity appears only when a disruption occurs, which may not happen for years. The trade-off between efficiency and resilience is not a technical problem. It is a temporal problem. Efficiency benefits are measured now. Resilience benefits are measured only when conditions change. When a major disruption reaches a zero-buffer chain, the cascade does not stop at the first facility. It propagates downstream at the rate of depletion, one tier at a time, until every dependent node is empty. The cascade moves faster than recovery can be organized. By the time a response is coordinated, the depletion has reached the consumer-facing tier. Shelves empty before replacement stock can be sourced. Shortage visibility triggers the second wave of the bullwhip. Every tier upstream receives exaggerated orders again, each actor hedging against the shortage by requesting more than needed. The system has entered its second oscillation. Recovery and overshoot follow the same logic as the initial disruption. For the same structural reasons, the mechanism does not learn. It repeats. Visibility into the chain exists at each tier only for the tier directly adjacent to it. A manufacturer sees its supplier and its customer. It does not see the full chain. No single node holds the complete picture. Shared data systems between chain tiers exist. When they are implemented, bullwhip amplitude decreases measurably. Most chains have not implemented them across all tiers. The gaps persist where the cost of sharing exceeds the perceived benefit. The chain's fragility is not distributed evenly. It concentrates at the points where buffers were removed first, where redundancy was eliminated earliest, where tiers are most tightly coupled. Strain accumulates without announcement. It becomes visible only when the component that was absorbing it reaches its limit. The limit is not marked anywhere in the system's design. Maintenance cycles were also optimized. Predictive maintenance replaced scheduled maintenance. Equipment is serviced only when sensors indicate a threshold is approaching, not at regular intervals. Predictive maintenance works well for failure modes that sensors can detect. It does not work for failure modes that sensors were not designed to measure. The unmeasured mode still occurs on its own schedule. The anchor facility now runs at reduced load. Its structure is unchanged. Its throughput capacity has not been rebuilt. What changed was the volume passing through it, not the vulnerability inside it. Recovery from a supply chain disruption is measured in the return of throughput TOT. It is not measured in the restoration of buffer, the rebuilding of redundancy, or the addition of slack. Recovery looks complete before it is complete. The system that emerges from disruption is not more resilient than the system that entered it. It returns to the same structural configuration, because that configuration is what optimization pressure demands. There are supply chains designed with distributed sourcing, regional buffers, and deliberate redundancy. They carry higher operational costs. They also produce smaller oscillations when disrupted. Both facts are true simultaneously. The distributed design is not inherently better. It is better under specific conditions. High disruption frequency, variable demand, long recovery times. Under stable conditions, the lean design outperforms it. The conditions that determine which design performs better are themselves not stable. The frequency and severity of disruptions changes over time. The design chosen during a stable period may be wrong for the period that followed. Regional disruptions have become more frequent across the period when lean supply chains became dominant. The disruptions did not cause the adoption of lean methods. The lean methods did not cause the disruptions. Both trends arrived together and interact. Transportation infrastructure that supply chains depend on was also not built with redundancy as a design principle. A single bridge closure, port closure, or rail disruption removes a path the chain does not have a substitute for. The compounding of physical infrastructure fragility with supply chain fragility is not an accident. Both systems were optimized under the same pressure toward efficiency and away from reserve capacity. Coupling between systems means that a failure in one system creates conditions for failure in the adjacent system. The coupling was not a design goal. It was a consequence of independent optimizations arriving at the same structure. The global supply chain, as it exists now, is the output of millions of independent optimization decisions made under competitive pressure. No single actor designed it. No central plan produced its structure. The structure that emerged from independent optimization is not anyone's responsibility to change. Each participant is optimizing correctly within their own constraints. The system-level outcome is produced by the interaction, not by any individual actor. System-level redesign requires coordination across actors who each benefit from the current configuration. The actor who holds the most buffer carries the most cost. The actor who holds the least buffer receives the most risk. The distribution is not symmetric. The anchor facility is running again at normal throughput. Its conveyors are loaded. Its junction is cycling. Its utilization rate is close to maximum. The conditions that produced the earlier disruption are fully restored. The system is stable. It is processing at full capacity. It has no buffer. It has no reserve. It has no redundant source. It is indistinguishable from the system that existed before the disruption began.